Hi and welcome to another MoTeC webinar. My name's Pete Swinney and this is part 6 of our introduction into M1 diesel tuning. So topics for today. We're going through pilot and post pulses. We've talked about those in previous webinars, but just a little bit more in depth and just to reaffirm what you've learned so far. Air mass measurement, so airflow meters and the channels that are involved in the ECU to do with that, and how to scale up to a larger airflow meter if you're going to fit something different. Maybe take an air mass meter element apart and put that element into a larger pipe. So we'll cover off how to do that and how to change the calibration. A little bit about engine speed limits and how that affects the fueling, and a little bit about idle control, just overviews on both of those. Just again to introduce you to the channels involved and just show you roughly how they work. That's it for today, so hopefully it won't be too long for you, and we'll keep going. Alright, so pilot and post. So again, we've got 4 pulses available to us in an M1. We have pulse number 1, which is usually called our pilot 1 pulse. Pulse number 2 is the second pilot. The third pulse is your main, and the fourth pulse is the post. Now I've got a picture here for you to look at. This is a capture of in tune where we've just frozen the data using the pause function. And if we go through it, just so you can see this as I talk, what all the lines are and mean. So on our top panel here we have engine speed, okay, and effectively this is just idling at 900 odd revs while I did this capture. And while I was doing this capture, I was adjusting the timing of the first pilot pulse. I wanted to show you how that looks. So this is a really nice feature in the M1 ECU where you can actually see the beginning and end of each pulse for the 4 available pulses. So in this case we're just showing you the 3 power driving pulses, or the 3 that are used for power, not the post. So our light blue lines here is the first pilot, and so the first line is the beginning and the end. So you can see that I've got a reasonably consistent amount or mass of fuel here while I'm doing this test, and you can see that on our vertical axis of this panel here, this is actually degrees before top dead center. Okay, so this is up to 55, 60 odd degrees before top dead center, and the panel goes down to about -7. Alright, so you can see at the end of this short test there that I've ended up with something like the beginning of the first pilot at 60 before top dead center, which is quite early, and the end of it something like 55, thereabouts. Alright, and where the cursor is at the moment, the actual numbers are the pilot 1 starts at 50.7, ends at 48.5. The next pilot, which you can see isn't changing in time, so the timing's not changing on that next pilot. It's a similar amount of fuel being injected over a similar time. So that's beginning at 26 before and ending at 23 before. And then the main pulse is starting at 2.2 before and ending just after top dead center. So you can actually see that all 3 are very similar amounts, and this spread of the fuel helps to take away that noise that we associate with diesel combustion, real sharp clattery noise, and the 2 pilots really smooth out that final sharp pressure rise that can occur if you just have a main. So this makes a significant difference on the noise, and so playing with the volumes or the mass fuel amounts in each of these pilots and their locations is what you do to reduce your combustion noise from under the bonnet. Alright, so, and the last panel at the bottom here, we've got our actual pulse widths, just like what you'd imagine you would see if it was a petrol engine. Of course, with a petrol you only see 1. So we can see our the actual pulse widths themselves, not in degrees this time, but in actual milliseconds. So 0.41, 0.52 and 0.46. So they are quite similar. Alright, and of course our fourth post pulse, there's nothing, we've got nothing configured that, so it doesn't show up. Alright, so after going through that, I think you get what our 4 pulses are for, and just to reinforce that again, the first 3 are what you use for making the engine power, and are generally pretty close to, well, certainly in general the normal tuning procedure is that they would all start, and certainly all start before top dead center. The main might finish after top dead center if the pulse widths are long, but they certainly would all start before top dead center on their injector timing beginning. Okay, and the fourth pulse, which isn't for creating engine power, is the post pulse, and that's designed for spooling turbos, burning off diesel particulate filters, emissions in general. And so to carry that through to what the actual ECU does with these pulses, the ECU will make a calculation for the amount of volume of fuel that you want to have delivered to the engine, and then depending on what you've got configured will distribute that fuel out amongst these three pulses if they're configured. Now, if for example I did something silly here way back at the beginning here, I could have maybe made the first pulse timing let's say 26, for it to start at 26 before, or 27 before top dead center. You could imagine that that would then run the end of the first pulse width into the beginning of the second. Now that can't, the injector physically can't open and close and deliver 2 precise volumes of fuel in that time. So what it will do is skip one of the pulses. I can't actually tell you which one it will skip. I assume the second. So it will skip that second. Now, instead of just missing that fuel and the engine power dropping, the fuel that is in the skipped pilot is then added into the main pulse width. So if we were to drop a pilot out on this, on say the second pilot out, then the pulse width and the injector time would change. This line would go down for the longer pulse width. It would be injecting for a longer amount of time. So you would see those 2 values change, and the engine would continue to make the same power in theory. And all of that works well provided we've got good injector calibrations, and I'll talk about that in a second again. Alright, so that's the idea of the 4 pulses. Again, three for making power, 2 pilots, 1 main, and then the 4th one for making boost. Alright, so when do we use them? I think you've picked up enough in the last few webinars that we're using our pilots to reduce noise, and really not much else. You can certainly help the engine start better. It's like a little miniature glow plug, a pilot pulse. So one of the other, apart from reducing noise, the other key part of a pilot's value to us is to help the engine start. So, and the reason that a pilot pulse is better at doing it than the main pulse necessarily is it is such a small volume of fuel. Often the main pulse might be, say, 10, 20, 15 microliters, and you can put in a 2 microliter pulse on a pilot earlier in the slot cycle, and because it's such a small amount of fuel, it will actually light a lot easier than kind of quenching the chamber out with a larger amount of fuel. So a little puff of fuel, say at 15 degrees before top dead center, that will light off, and then when the main amount of fuel comes in, we've already got the chamber a fair bit hotter than what it would have been just from cranking compression, and that will help that initial lot of main fuel burn a lot quicker, reduce smoke, things like that. It makes a big difference when it's cold. Alright, so I've covered off those other two volumes and timing, about what we're doing with those pulses there. So, and as I said before, injector calibrations have a big effect on how well this whole pilot system works. So if we have a variation in our injector calibrations, which we kind of realize is going to happen due to the manufacturing tolerances of diesel injectors, then what that means is if we're getting down to very, very small pilot pulses and very small pulse widths, then we can get scenarios where the engine thinks it's delivering fuel and potentially isn't delivering fuel on some injectors, so you get drivability, very minor drivability admittedly, but drivability issues with that, associated with that fact that we don't know precisely and very, very accurately the flow of each injector in every cylinder. Now, one of the ways to actually help that, if you've started tuning your diesel and you're struggling with getting pilots to stay working, the first kind of global overall rule with pilots is to keep them separated so they don't run into one another, and configuring up your in the timing worksheet, I believe you'll find, and I think it's the pilot one, or if not the main one, you'll see a worksheet configured with a screen similar to this. So you can keep in mind that trying to have the second pilot run into the main, or the first pilot running into the second, is going to cause things to skip anyway, and whenever a pilot skipped, you have the potential for a small power change if the injector calibrations aren't right. So we want to try and always keep a pilot going, and I would suggest initially at least you just start working with one pilot. There's not many vehicles we've actually gone to the trouble of getting the second pilot in, and in the motorsport world really you don't need any other than starting. It's certainly nice to have at least one for the engine to run quietly if it's got a standard exhaust system on it. But certainly the second pilot is probably getting into the more advanced parts of the diesel tuning, so don't panic if you can't quite get that right. So, but one of the keys to making it easier for the pilot pulse not to drop in and out due to injector calibration issues is to have the pulse widths that is delivering that volume of fuel, let's say 5 microliters. If you have the pulse width longer and further away from the dead time, then you've got more room for error, if you like. And so the way to make the pulse width longer for the same amount of fuel is to drop the fuel pressure. So you'll find by dropping the fuel pressure lower than perhaps maybe the OE runs it. So for example, OE might run it at 40 MPa. If you drop yours to 30 MPa, then that's something that will deliver the same amount of fuel if your injector calibration slope is right, but the pulse width will be longer. So in this example we might have, I haven't actually got the volumes of fuel being delivered on the screen, but by dropping the fuel pressure 10 MPa, we could probably, the pulse width is probably going to extend something like 50 microseconds, so 0.05 milliseconds, and that's enough to make quite a difference when it comes to delivering those small amounts of fuel and getting further away from your injector dead time. Now, we spoke about the dead time and the reasons to stay away from that in a previous webinar, so if you haven't seen that, I'd suggest you go back and have a look. Alright, so that's the basic overview on pilot and post pulses. In future webinars we'll go through that live, but for now that's just an overview of what they do. Alright, the next one is mass flow versus engine efficiency. So right back at the beginning, I think we spoke about trying to determine all our M1 ECUs try and accurately determine the exact amount of fuel going into the engine and the exact amount of air going into the engine. If we can do that accurately, then the ECU knows within its own calculations, without even measuring lambda via a sensor, what the lambda would be. If it knows the airflow and knows the lambda, it therefore knows, if it knows the airflow and the fuel flow, then it therefore knows what the air to fuel ratio is, which converts to lambda. So in the diesel project, we actually have as a channel that you can view the lambda estimate. So that is what the ECU thinks the current air-fuel ratio is. Now it does that calculation based on the amount of fuel it thinks is going in and the amount of air it thinks is going in. So I know we keep talking about this, but we're back to injector calibrations. If we had dead accurate injector calibrations, then it's quite simple to if the lambda was wrong as we were tuning it, then the only reason the lambda would be wrong is because the ECU's calculation of airflow was wrong. Because we can't 100% rely on our fuel input calibration, our injector calibration, we therefore then, if we have an error in our lambda, we don't know whether that's coming from the ECU's estimate of, or the ECU's calculation of the air that's going in, or the ECU's calculation of the fuel that's going in. So to make it easier for us and to help things line up, if at all possible, then we'll try and use a physical sensor to measure the air that's coming in. So in most cases that sensor is going to be an air mass meter. So certainly all the modern diesels that we've seen all have air mass meters on them, and as a way of determining the volume and the weight of the air entering the engine. The reason a map sensor doesn't work using like a speed density style calculation is because the majority of diesels have variable nozzle turbos on them, and those variable nozzle turbos can have, at any given consistent boost point, can have a very high exhaust back pressure, creating very low airflow or bad engine efficiency, or they can have at that same boost point the vanes on the turbo can be open because there's a higher volume of fuel being entered, and so if those vanes are open and the exhaust back pressure is low, you then have a way more efficient engine. It flows more air. So what that means in effect is that manifold pressure is not, in a diesel engine, is not really a good way of determining a consistent and plottable, repeatable airflow. So for that reason, we suggest, you don't have to, but we suggest to help line things up and make your tuning job easier, you use an air mass meter to do that. Alright, so opening statement, mass flow is everything, and it really does make your life a lot easier. So let's explain the graph you see in front of you now. So we've got engine speed on the climb here. I have some boost going up and down, or manifold pressure you'll see is rising up and down. Currently where the cursor is, it's 315 kPa, so that's just over 2 bar of boost. Nothing too dramatic for a diesel to see that. And then I have my air box mass flow. So this is my mass flow sensor, and so this is in grams per second, and you'll see, hello, what's going on here? We've got some gaps where the sensor output stops, or so our graph stops, and we have in these areas where we have no line, if you click in there, that actually is called not a number, NaN, and so if the air mass meter goes into error, then the channel can't give us the reading. There's no fallback for it. For the air mass flow, we can't estimate what it'll be, so we don't have a fallback as such for an air mass flow fallback channel. So if the air mass flow goes into error, and in this case it's very common to see this, I would suggest you, as soon as you start performance tuning a diesel, this is one of the things you will look at straight away, and that's to make sure that the air box mass flow is giving you a consistent and continuous output reading. So once it gets to the end of the calibration, the sensor goes into error, and we get no more reading from that sensor itself. So what happens in the ECU? It's not just going to leave us hanging there, that's for sure. We actually, when the air box mass flow sensor tops out, it then reverts back to using the engine efficiency map as its means of calculating airflow, or the engine charge is actually what it's called. And we looked at that in a previous webinar, where engine charge is actually calculated in milligrams, so it's a physical mass or a weight of air that's going in. So in our example here, we have, while the air mass meter is live and hopefully it's calibrated well, the flow is in grams per second, and the ECU converts that by measuring the air temperature and the flow, and it comes out with a physical actual amount of weight per cycle, and that becomes our engine charge channel. So if you can see back where my arrow is, right at the beginning of this capture here, you will see we've got two lines. We've got the green line, and then above that the red line. So the green line is the actual engine charge as derived from the air mass flow meter in milligrams. And again, if that's accurate, if the calibration's accurate, then that's pretty much the air that's flowing into the engine. If we know the fuel that's flowing in milligrams, we divide the two together and we've got ourselves an accurate air-fuel ratio. And if we convert that to lambda, then that is the lambda estimate channel. It is engine charge divided by fuel volume, or mass fuel volume, the mass fuel that's going into the engine, and then you divide those one into the other and you get an air fuel ratio of, say, something like 22:1, which converts to a lambda of, I don't know, 2:1 or something like that. Alright, now while the air mass meter is giving us good data, that's the process that the ECU uses to calculate the amount of air that's flowing. Now the moment that air mass meter tops out, the ECU then uses the engine charge estimate channel as its calculation for airflow, and the engine charge estimate channel is derived from our air temperature and our efficiency map. Alright, so our efficiency map, like we used to tune with our petrol engine, is still used, but only as a fallback if the air mass flow meter's not being used. So if you think about that, you don't have to have an airflow meter for this whole system to calculate airflow, but what you do have to do is then tune the efficiency map to make the lambda accurate. And as discussed earlier, the efficiency map will continue to change depending on the position virtually of the variable vane turbo if you've got one. So the VNT, the position of the vanes in the VNT, the variable nozzle turbo, will affect the exhaust back pressure, which will affect the efficiency. Now, and that change can happen at one consistent boost pressure. If we add fuel to maintain the same boost pressure, the vanes will need to open, and that will reduce the back pressure and increase the flow, which is kind of nice. It means we can add more fuel if we've got more airflow, which means if we add more fuel, we can open up the vanes more, and we have this wonderful cycle where if we add fuel, we open the vanes, and the whole thing spirals up. Alright, but back to our problem. So no airflow meter means engine charge estimate channel is used. Engine charge estimate channel is the result of your efficiency map, which we realistically should recognize is difficult to get accurate, and therefore we see an error happening. So I've mapped a lot of engines and kept updating the engine efficiency table so that these lines continue to match, and after the variable nozzle turbo you go through a series of updates and the tune is pretty much finalized, then you get reasonably repeatable vane position for any given volume of fuel and any given operating point, and you can get the engine efficiency table quite close. So if you see where the mouse is now, you can see that our calculated airflow from the efficiency table and our actual airflow derived from the mass flow meter are virtually identical. So it's good policy to keep updating your efficiency table and keep correcting it to try and keep these lines together, so that if it does drop out, if you do have a problem with the air mass meter, if you run some more boost and you run out of air mass meter, then when that switching point happens, when you go from having an air mass meter to not having an air mass meter, you don't want the situation that you see here where we get a big change in the engine's calculation of airflow. Now that change you will feel as a change in power. Alright, so the lambda will change, and if there's anything, actually it won't change in power as long as the fueling changes, but what this changes is the vertical axis of the smoke map and the vertical axis of the fuel mixture minimum map. So this engine charge channel is used in a lot of fuel maps, so you can get a fueling change, not always, but you can get a fueling change if this engine charge channel changes. Alright, I hope that wasn't too confusing. So we need to avoid this in the long term. We want these lines to be as close as possible. Now, the ultimate way of avoiding this, of course, is don't have this happen. Ultimately that's what I'm leading up to, is if the EMS meter never drops out due to running out of calibration or running out of flow range, then you'll never get a situation like this. So the mass meter right at the beginning of our tuning is going to be a consideration. So, is your sensor big enough? My rule at the beginning of this path is basically if you're running any more than, or intend to run any more than 30 or 40% more airflow or more power than what the stock engine has been set up to run, then you're going to potentially run, the stock mass flow meter is going to be running out. It's pretty similar to petrol engines, to be honest. So your average petrol turbo car was probably running out around 20 or 30% more power or more boost. You probably talked about in those days. So if you're intending to double the output of this diesel engine, which is quite common to do, then you can pretty much guarantee that the airflow meter that's on the engine from factory won't be big enough. So don't wait for it to run out and then try and deal with it halfway through a dyno tuning session. Deal with it at the beginning, and if you can work out kind of the flow rate increases you're going to achieve, then you can actually remove, in most cases you can actually size the whole thing up by removing the element out of the EMS meter and putting it into a larger diameter pipe. Alright, so what this effectively just makes it still read something at the higher flow rates. It's better to have a reading EMS meter that's at least repeatable, even if the numbers aren't super accurate. Alright, so that's the first point of call, or what I would do anyway if I had a standard engine and I was going to significantly increase the power. I would take the element out, work out kind of how much bigger I was going to, how much more power I was going to make, and increase the flow of the airflow meter appropriately. Alright, so just to cover off why, I think you understand why and how the ECU uses this sensor, but again, just to reinforce that it's using that engine charge estimate channel on the vertical axis of the fuel mixture minimum table, and that table effectively is the table that you'll end up using, I'd suggest, to control your smoke. And then we do have that smoke table itself as well, which is named smoke, and the vertical axis of that channel, of that table, is also engine charge estimate. So they're the two main fuel related tables that use the EMS meter, or the engine's calculation of airflow, on those tables. Okay, if you're not using those tables, then it simply becomes as you've probably seen in the previous webinar, the whole fuel system and the fuel model just basically works on pedal position and multiplied by the fuel mass limit table. So that whatever's in the fuel mass limit table at the particular operating point, multiply that by the percentage of where the pedal is. So and that pedal percentage table, of course, is called the nominal table. It's the nominal fuel mass. So if it was dead linear, where 0 at the bottom and 100 at the top, at 50% pedal, we'd be asking for 50% of our fuel. And if we had 100 milligrams in our fuel mass limit table, we'd be requesting 50 milligrams of fuel. And if we didn't have anything configured in this smoke table, fuel mixture minimum table, any of those other fuel limit tables, then we would simply deliver 50 milligrams of fuel whether the boost was there to burn it or not. The problem is if the boost wasn't there and we go richer than our lambda of, say, 1.1, we'll smoke the whole shop out. Maybe that's something you want to do, no problem. Generally today that's not what we're after. Alright, so I think that's reasonably clear. I hope so. So again, that's just that last point there, just saying if the air mass meter's dropped out, it's either not there, broken wire, or run out of range, then we're using our efficiency map as the calculation point. Alright, so many people asked, well, okay, you tell us to scale this mass flow meter up, how do we do it? So here's the process you're going through. You're going to make an estimation of the extra airflow required, and you can do that using your diameters to see what your increase is. So if you look at not the diameter, the area of the pipe. So in our example, we are going to calculate the area of a 58 millimeter factory airflow meter. So that is simply pi r squared. So the calculation goes 58 times pi times radius, which comes up with 2,642 square millimeters. If we, for example, want to choose, and let's say, hey, I'm going to grab a piece of 3-inch aluminium pipe and drop my element in there, and that's 75 millimeters on the inside. So then the flow, or the area calculation for that pipe is pi times radius, which is 4,418, and if we divide one into the other, we get a percentage of how much more airflow, or how much larger, well, it's actually airflow in this case, how much larger the area of that our new produced or manufactured airflow meter is going to be. So in this case, it's going to flow 1.67 times more air, or nearly 70% more air. So possibly 80% more air than factory, depending on too many things to go into. Alright, so we then take that number of 1.67 times more air, and how do we put that in our calibration? So our next page will show you that. So here's our mass flow scaling. Now I'll just quickly go back as to how you might derive this even on the factory airflow meter if you haven't got a good calibration from us, or a known calibration for the airflow meter you're doing. There's really only a couple of ways. One of them is if you connect in series an airflow meter with a known calibration. You can simply go to each operating point in the engine's airflow range and observe what, say, the Bosch airflow meter says is the current grams per second, and then enter it in your calibration. So that's one way, and it's one method we use. The other method is if you do have the luxury of having a standard vehicle that you're working on with an OBD2 port. So any late model vehicle today has OBD2, and you can just pop a scan tool into that OBD2 socket, and in most cases, most vehicles will have, you can see what the airflow meter output is. So we can actually sit there, maybe free rev the engine and say, oh, we can look at the scan tool and say, right, this is flowing, let's say 26 grams per second. And then if it's, depending on which type of airflow meter it is, if it's an analog volt output airflow meter, at that same time, if it's not on the OBD2 channel, the voltage isn't on the channel that we can read, we can simply put a multimeter on it or log it. So we can look and manually look at which voltage, in this case it's voltage, which voltage is giving us what grams per second airflow, and we can simply plot our curve looking like that. If you get a few random points that don't appear to be right, I mean, a mass flow calibration should look something like this. It should have kind of a parabolic curve to it, not quite, but certainly a curve, something similar, and it should be smooth. So if you do get some random points, chances are they're going to be wrong, so you're better to pop them back down and do a reasonable curve fit to make a consistent curve. Alright, so if this was our standard mass flow calibration and it was hopefully accurate, and then we take that element out of that standard mass flow meter that we had, so we're going out of a 58 mil, let's say Mitsubishi Triton mass flow meter, and we're going to put a bigger turbo on this thing. And so my suggestion for anything up to about 350, maybe 400 horsepower, but somewhere around that kind of airflow, you should be able to get away with a 3-inch pipe, around that 75mm pipe, as your new mass flow meter. Now you can of course buy your own mass flow meter. Again, as we covered in a previous webinar, there are some that are available. Edelbrock sells one. That's large, it's at 4-inch. But you really want to size the mass flow meter to be just big enough to do the horsepower range that you're going to cover. And it's a bit like sizing a map sensor correctly for an engine when you're going to run a particular amount of boost. It's the same with the mass flow meter. It's even more important with that. So we don't want it too big, because mass flows down at the lower engine speeds and things are going to be inaccurate because of the low actual flow through the large diameter pipe. So long story short, I'm sure you've worked it out by now. We simply take all of those numbers and we can just go Control A, which will capture all of them, and then just go on our keyboard equals, multiply 1.67 and enter, and then the numbers will all just go up by that factor. And that's our new calibration for our new mass flow meter. Right, so you can see I went to a reasonable amount of effort to explain how to do that, and I hope you take from that the reason I've done that is because we think it's important that you get that right. You will be able to get this thing tuned without any of it, and it'll be okay. It might be a bit, a bit surgy when it clicks in and out of things. We'd rather you did it right and the engine ran nice and everyone was happy. So please take that on and try and do that work before you get to the dyno. It's much easier than interrupting things and breaking away and doing it afterwards. Alright, so 2 more things to go: engine speed limit and idle control. And again, these are just overviews. The engine speed limit function in the diesel package is actually quite complicated when we dig in really deep. We're not going to do that today. In most cases it just works. There's really 2 major ways you can run it, and as you can see on the screen, we've got cut, so cut only, or fuel mass reduction. So cut only works just like you'd expect, just like a petrol engine where we physically turn off injectors and do fuel cut to maintain the limit. Now that's actually not an ideal thing to do. It does give us very reasonably precise control, and it's under all operating conditions it'll always work quite well, but it comes with a set of problems associated to it. And so those problems are highlighted in this first capture here in front of you where my mouse is running around. So let's have a look at the channels. We've got our engine speed limit here, in this case 3000 revs, and we've got our engine speed rising up here, and then it's configured to cut only, and effectively it overshoots and cuts and overshoots and cuts, and we get quite actually an aggressive engine speed limit control. And in this particular case it's aggressive not only because it's aggressive when it's cutting a quarter of the cylinder, like ignition cut, but the main problem in this case here is coming from our fuel pressure control. So it's quite difficult for the fuel pressure system to control a dead end rail system that a common rail diesel injection or fuel system is a dead end system. So controlling the fuel pressure very accurately in there with no general return and very, very high fuel pressures involved, it's quite difficult to get highly accurate pressure control. So we've got a couple of issues here. So the first one we've got is our aim is swinging around from our engine speed dropping up and down. Now that can be fixed by making the fuel pressure in and around this area a lot smoother, the fuel pressure aim. right? So that's the first thing. But the other thing is that when a diesel injector cuts, the fuel rail pressure spikes because it's the ECU is expecting the fuel to be going out of the injector, and it doesn't. It stops, the flow stops instantly, and it causes a pressure spike, and then the PID system, in a lot of cases struggles to deal with that. The fact is that it doesn't, there's no return. It doesn't blow out. That extra pressure spike doesn't lift an ordinary pressure regulator like on a petrol engine. And the hammering effect of the injectors opening and closing quickly makes that whole fuel pressure control really quite difficult. Now, you can get it right, but it's certainly one of the downsides of doing cut only. And so in most cases I suggest, unless you need to do this method, then you certainly don't start with it. Now, all our start files will be on the other method, which is fuel mass reduction. And certainly I'm not aware of any OEs doing cut, but maybe they do after a certain pressure's really or a certain engine speed's been reached. But the vast majority of engine speed limiting that I've seen, including our own in the start files, is simply fuel mass reduction as a method of controlling engine speed. Right, so let's have a look at how that works. It's pretty simple when you think about it. So on our second capture here, we can see our engine speed limit is 4,000. Sorry, it's got a color change on us. So that's the green line here. Here's our engine speed coming up. And so this system, you can change how it operates in some of these parameters, but basically the ECU looks at the engine speed in relation to the limit, and when it sees that it's approaching close to the limit, and the faster it's approaching, in other words, the more vertical the engine speed line is, the more fuel it actually starts peeling out prior to the engine speed limit even being reached. So what this is doing is giving you a very, very soft engine speed limit. It's in fact dead soft. It's just like you took your foot off at exactly the right time. And so there are two aspects to this particular function, as far as you can program the amount of soft coming into how soft it comes into the engine speed limit. And you can program, or you can obviously program the engine speed limit itself, and you can also program the amount of overshoot you'll accept before you actually allow cut. There's lots of things to program, but in most cases you don't have a large overshoot. You can have a large overshoot if you don't allow any, what I'll call, undershoot. So if you say, I don't want to be any fuel mass reduction until I reach the rev limiter, then you can expect that you're going to get some overshoot as the fuel mass begins to reduce only after we start going over. So the ECU can only reduce the fuel at a certain rate. So if the engine speed limit, or if the engine speed is raising very, very, very quickly, then you will get higher overshoots if you don't have a softer undershoot time. I know they're not the exact terms. I'd have to look them up. I'm sorry about that. But the engine speed limit parameters, there are a lot, and it is quite complex to get into tuning this in fine detail. But to date, other than a couple of really high-end racing applications, I've never had to change this. So basically set the engine speed limit where you want it and it will just work. So here's what's actually happening with the fuel mass itself. So our fuel mass being delivered to the engine is the blue line. It's the one we've got clicked on. So this is the throttle pedal and engine speed all affecting the fuel mass. So you can see the driver has requested more fuel via the pedal, and here's the fuel coming up. Engine speed's coming up and approaching the engine speed limit. And once it gets to a point where it gets within a band that you can specify underneath, where it's underneath the engine speed limit itself, and it starts to reduce the amount of fuel mass, anticipating that the engine speed is going to hit the limit. So in this particular case, you can see I've shown here the pink line is where the engine speed limit has become the influencer of the fuel mass. So at this point here, the engine speed limit system is the lowest fuel mass out of all those tables that we went through in the fuel model. A couple of webinars ago, we went through the whole fuel model, and then the fuel model dictates that if any of the tables, the fuel mass limit tables, has the lowest number, then that number is the winner, and the fuel mass then becomes the same as the lowest number of any of the tables. So in this case, the engine speed limit calculates that you need to pull fuel out to stop it over revving, and then as the engine speed gets closer and closer to the actual engine speed limit, that calculation calculates that the fuel has to come further and further and further out. So for this time here, the pink line is the lowest number, and it's not till the driver gets right off the pedal that the pedal then determines that the fuel mass going into the engine needs to be even less. So from this point to this point, the engine speed limit system is controlling the fuel mass. Now, without having to look at pretty lines and things, we can tell here that by looking at our fuel mass limit source, at the point that it switches from, if I click down here, if we were live, it would say fuel mass unlimited, or the pedal, one of those two. And in the moment the engine speed function or system determines a lower fuel mass than what our pedal's determining, then the fuel mass limit source switches to engine speed. Alright, lots of engine speed words in there. Alright, so again, it's an overview. It is quite detailed and quite complex if you want to dig into it really well. Some nice features in there if you really want to maximize the benefit of the engine speed limit. Some people might be willing to accept a few hundred over revs and want full power all the way to the rev limit. Well, you can do that. Other people, OEs and things, want a nice soft engine speed limit. They don't want the thing to rev any more than what they've got it designed to, especially with a diesel with heavy rods and things. They don't want the rotating mass to be going much more than the desired aim. So all sorts of, as I say, parameters in there that you can customize and adjust to get the behavior you want. And we may in the future go do a sole dedicated webinar on that, so you can look at it. But just for now, that's the overview. Alright, idle control. It's actually a similar story here. This just works. It works spectacularly well. So much better than a petrol engine. And there's a couple of reasons for that. The first thing to let you know though is it's very similar as far as the basic setup is the same as the petrol idle control. You've got some parameters that tell you when the pedal position is below a certain amount. That's when you should go into idle control. You have the ramp offset and the ramp down rates are all similar, so all your aims are very similar. One of the reasons though that works so well is that we don't generally have unstable ignition affecting our idle. We don't have to get our lambda or our air fuel ratio in a good area in a diesel for it to have for it to run stable. So what I mean by that is, in a petrol, if we want our engine to idle nicely, no point in doing idle control until the engine is tuned properly, until the ignition is stable, until our lambda is somewhere between 0.80 and 1. If our engine on a petrol engine is running at lambda 1.1, it doesn't matter how good our idle control is, the engine itself has got poor combustion, so it's difficult for it to idle well. With a diesel, doesn't matter what the air fuel ratio is, it always wants to idle smoothly. Its idle stability doesn't rely on air fuel ratio. It just burns the fuel that's delivered, and that's it. There's obviously exceptions to that, but we don't have that as much as petrol affecting what's going on. So with a diesel, as we've said all the way through here, your power at the engine, at the crankshaft, is determined by fuel. It's affected a little bit by air, but not that much. Basically, add 5% fuel, get 5% power. Take 5% fuel out, lose 5% power. So what that means is the ECU has really good control of the amount of power it makes under idle control situations. So if it wants to lift, it can calculate on the fly very quickly if it's under or over the aim, and it very quickly can change the amount of fuel, and you get on a diesel a very quick response. It's not like a petrol where you get a quite a sluggish response to a butterfly, an airflow, a throttle opening and closing. With a diesel, it's fuel, it's directly injected, and you get an instant response, after the ECU makes the decision to add or subtract fuel. So as a result, you've got to do some pretty wrong things to get this thing not to idle. It pretty much will always idle. But here's a couple of key things to look at if it's not idling correctly. So here's some channels I put on that are going to be for you to look at. So starting at the top, we've got our engine speed in orange and our idle aim. Alright, so, and you can see we're right on 800, and you can see here that the two lines are just about overlaid, and the scalings, it's not as if the scaling's out to 10,000 revs, it's reasonably tight on the scaling. So just about always, whenever we're looking at anything to do with diesel, you're going to want to see the fuel mass. So the fuel mass is in blue here, and then we've got some other fuel masses. So we've got our idle fuel mass. So this is the fuel mass. Once you're in idle control, the fuel mass delivered to the injectors is derived from the idle fuel mass volume. So you can see here the two lines are overlaid. The reason you can't see blue here is because the whatever color that is, light brown, light greens, light something, that color channel, that is deriving our fuel mass. Now, just before we go any further, see how our fuel mass is going up. This test was done in a manual in our Hilux, and it's a manual, and I was just quietly pulling on the clutch here. So I was manually dragging the engine down, simulating, some sort of a problem with the engine. So I'm forcing the engine speed under the aim and just showing you what happens to the fuel mass and these other parameters to help get the engine speed up again. Depending on how you configure your tables and your minimums and your maximums, you can actually almost even in idle control, you can get a situation where you can have the thing virtually tow a trailer up a hill in idle control, because if you don't put some sort of a clamp on the amount of fuel it can add, then it will simply just keep adding fuel until it meets its aim. So if you apply more load, it'll add more fuel. If you apply more load, it'll just keep adding and adding and adding fuel to get that engine speed up to 800 revs. So you literally can get almost the full amount of fuel that's available within the limit system into the engine, and to prevent stalling. Alright, so going back to the channels though, so again blue, this is ultimately what's going to the injectors. In our case here, while it's in idle control, if we go down to the bottom here, we can see our idle state is enabled. So when we fell down into idle control under our aim idle, and that's our ramp offset up here at 1300, as soon as our idle control enabled, our state went from disabled, can't remember what it would be when it's not enabled, and into enabled. So once it's in enabled, that means the throttle is off and we're running in closed loop mode. And so in closed loop mode, like most closed loop systems that we have PID parameters or PID channels that are operating to influence how that fuel is applied to get us where we need to be. So just so you can see it here, so again, this is the idle fuel mass is the result of all the calculations. It's the final result that the ECU is delivering off to the main fuel mass channel to deliver to the injectors, and that idle fuel mass is calculated from the integral, proportional, and derivative, feed forward, no derivative in this case. So we have a feed forward idle fuel mass number, and I know we're getting a little bit deep here, but if you're having trouble with idle control, you can come back to this webinar and study. And now the idle mass feed forward, see we have a number of 2 here, and see that's actually quite consistent through this test, and that number 2 is 2 milligrams, and that number comes from, if you can remember, the fuel mass minimum table. So whatever's in the fuel mass minimum table at this operating point, engine speed of 800 and whatever the current coolant temperature is, that is our starting point for our idle control. So when we click into idle control that very first time, it's going to be using 2 milligrams. From there, the proportional throws some fuel in or out depending on what's going on, proportional to the error, and the integral starts to wind in some fuel based on time. Now our current start files have quite a large integral number in them, and so what that means is it allows the ECU to, no matter really how bad this feed forward table number is, and no matter how bad even your injector calibrations are, this integral number will just wind in and out fuel to give you a stable idle reasonably quickly. And so I can't remember if we've got a clamp on it just as I do this webinar now, but in fact at early software I've actually asked for one from memory, but certainly our early software didn't. So you could actually end up, if you came into the screen where you can see your idle control, you can actually look at this channel, the integral channel, and see how far out your current idle your idle fuel mass feed forward numbers, or your fuel minimum table number is. And it's actually not a bad idea to, if it's a long way out, so in other words a very high integral number, then it's probably not a bad idea to update that, and that will help it snap into idle control a lot quicker. Alright, so in this case it's not too bad. The proportional's kind of fixed anything reasonably quickly, but you can see that it's not perfect. It's pushing a little bit of extra fuel in based on time, and at a guess, maybe, well, that's only 0.1 milligrams there. That's probably 10 times more, so it might be 1 or 2 milligrams out. Okay, so hopefully that makes sense. Last channel here, which is obvious, is the pedal. Obviously the pedal's at 0 while we're doing this, while our idle state is enabled. Alright, so for those that you know about PID, I think that's reasonably self-explanatory, and for those that don't, hopefully it's a little way towards learning a little bit more about it. Okay, so that's it for this webinar. Thanks for listening again. The next one, if you're carrying on, is our final benchtop one, if you like, and it's about just the workflow of how the process of tuning. Alright, so we'll catch you then if you tune on in. Cheers.